Welcome viewers, my name is Becher and I'll present our work on multi-attribute visualization and improved depth perception for the interactive analysis of 3D truss structures. This work is motivated by performance evaluation of design variants of truss structures being an important aspect in the architecture, engineering and construction domain. And since the topological layout of truss structures is directly related to its performance, it can be beneficial to researchers to view performance-relevant attributes directly in the spatial context of 3D rendering. To aid this, our goals are to reduce visual clutter and to improve depth perception for rendering 3D truss structures on the one hand, and on the other hand, to investigate possible approaches for visualizing multiple attributes on the elements of the structure directly. So of course there's quite some related work on both dense line rendering and multi-attribute visualization, and this is just a small selection. Before we take a look at rendering effects, let us briefly discuss the base rendering. The structure that we investigate are given as a set of nodes and a set of edges. We render each edge as a camera-facing quadrangle, and we render each node as a raycasted sphere with a base geometry again being two triangles. The first couple of rendering effects for improving depth perception that we will discuss are based on distance to the virtual camera or distance to a user-defined point of reference on the structure. To ease this effect in and out, we use a normalized distance value as it is defined here, which uses a user-defined maximum distance. Let's first take a look at the base rendering of an example structure without any effects. Clearly, there are some issues with visual clutter and understanding the exact topology of the structure. Using brightness attenuation, elements of the structures are more easily distinguished. Here, the brightness is attenuated relative to a selected element in red. The defocus effect puts a stronger highlight on the area around the selected elements, but keeps the complete structure fully visible. And lastly, we feature a width scaling effect, here now based on the distance to the camera. We feature two more effects that are not distance based. Depth dependent halos add a border stroke in the color of the background around each element. This border is rendered thinner if lines that overlap in screen space are in close proximity in Euclidean space, otherwise they become thicker. Finally, screen space ambient occlusion is a well-known effect in computer graphics that provides a very rough approximation of light occlusion due to surrounding geometry. For the multi-attribute visualizations, let's first briefly discuss the investigated data. For each structure, we are looking at its redundancy matrix, which gives information on the distribution of statical interdeterminacy as well as additional topological attributes. From this matrix, we get different per element values, such as the diagonal entry or the absolute column sum. The 3D rendering shown here, for example, has a diagonal entry value from the redundancy matrix in the upper right mapped to color. When rendering multiple attributes directly on the structure at the same time, we are faced with two challenges. First, the geometry of the structure is fixed and can only be changed to a very limited degree. Second, the available drawing area is very limited as the edges are generally rendered fairly thin. The first approach shown here maps values to the width of elements. This mapping can be a bit tricky as it overlaps with element width in screen space being depth dependent due to perspective projection of the camera. Next, the shape of element is modified with the frequency of curling being directly proportional to the values. For mapping values to color, we differentiate between two different mappings. Stroke color is limited to the border area of the elements as seen here. Fill color, on the other hand, is limited to the interior of elements. This allows us to provide two visual channels via color. Additionally to the mapping of different visual channels, we also provide the option to filter elements based on a given value. Filtered elements are not completely removed to keep the spatial context of the complete structure. And finally, we support different visual channels for rendering the nodes, namely node size and both stroke and fill color. Please note that for the nodes, the displayed values are usually aggregated from the adjacent edges using different operators. As a preliminary evaluation, we performed expert user interviews with 2 participants. Expert number 1 is a domain expert from architecture and focused mainly on getting insights for understanding the redundancy matrix. Expert number 2 is a visualization expert and commented mostly on the visualization techniques in general. Both experts could freely explore the application and no predefined tasks were given to them. As finding meaningful metrics and mappings for the investigated data is still subject to ongoing research, identifying relevant tasks is also one of the future goals. Both experts received guided briefings through the rendering options and the available attribute visualizations before continuing on their own. Here's some of the feedback the experts provided. For depth perception, they commented on depth halos to be useful to tell foreground and background elements apart. They found distance-based brightness to be slightly better for assessing the position of elements in 3D space, but noted that the effect also tends to hide some areas of the structure. Defocus, on the other hand, is good at retaining the full spatial context, but was visually taxing. Overall, both experts favored the use of distance-based brightness with screen space ambient occlusion. For multi-attribute visualization, the experts said that color is well suited to identify redundant elements and outliers in the structure, but commented that additionally viewing exact values would be beneficial for some tasks. Regarding shape modification, one expert noted that strong differences in shape can stand out prominently, however small differences in value are hard to recognize. The expert also noticed that mapping one attribute to multiple channels at the same time emphasizes discontinuities and homogeneous regions. Regarding general settings and filtering options, the experts prefer to reduce the base width of elements to put more emphasis on the nodes, and one expert suggested it might be useful to completely hide all edges as well. Having the options to set minimum and maximum width of elements was considered useful, and it should be available for more visual channels. Filtering was well received, but one expert noted that elements that had been filtered out still remained fairly noticeable and occluded other elements. Lastly, experts stated that filtering should also be available for the nodes and not just the elements. To conclude, we investigated several rendering effects that can improve depth perception and reduce visual clutter in the specific context of viewing 3D truss structures. We investigated multiple attribute visualizations directly on the elements and nodes, and found that the visual channels we currently provide are useful to indicate and identify interesting regions in the structure that should be investigated in greater detail. Our initial evaluation with 2 expert users provided valuable insights for possible improvements. In the future, we would like to refine the rendering effects and assess additional visual channels, and of course interview more experts and identify relevant tasks that can be supported by visualization.